The first one to guide us towards the solution of the quantum problems is Louis de Broglie. Everybody who uses quantum mechanics uses the Broglie wavelength relation, because everybody who uses quantum mechanics uses the Schrödinger equation or the Schrödinger operator definitions. And both of these use the Broglie's wavelength relation, as will be seen in the next part. The problems of quantum mechanics stem in a large part from misunderstandings of de Broglie's work, which is probably due to the rather intricate way he wrote it down. This will be improved upon here, but his physics will be kept intact and in fact be built upon. One of the conclusions will be that there is something wrong with one of the most cherished concepts of quantum mechanics, the wave-particle duality. So let's start. The point in time when de Broglie started his work was just after Bohr's introduction of the planetary model of the atom, which gave the first reasonable sounding explanation behind the discreteness of atomic spectra. The goal of de Broglie was to go a step further and find an oscillatory phenomenon that could explain the discreteness of these states. One can assume that he started with an example of quantization that he already knew of, that of musical instruments. Musical instruments produce discrete tones, or notes, by generating a more general oscillation, here by scratching with the bow over the strings, and then selecting separate notes by putting a boundary condition on them, here the length of the strings. Boundaries cause reflections of waves, and the interference of those with the original ones creates standing wave patterns, which are audible as specific notes. So how about trying to do something similar for the atom? Then the first thing you need is an oscillation. There the analogy doesn't work very well, because musical instruments start with a bunch of frequencies. For another example, the flute, clearly audible when you blow randomly into its mouthpiece. You get a hissing sound, and in the graph looks somewhat like the illustration. The separate notes come from the finite length, in this case defined by the holes in its pipe, and at the end of it. The problem is that you cannot readily find such a source for the atom. So de Broglie started with something that already had a definite frequency, which he found, and that's the crux of his model, by combining two already known basic concepts, the rest energy of Einstein and the quantization relation of Planck. However, if you search for an illustration to show with it here, using the Broglie equation, you get screen after screen after screen of wavelength relations. But that's absolutely not what de Broglie started with, nor what he got as a result of the calculations in the first and central chapter of his thesis that contains most of the calculations. The fact is that in this first chapter, de Broglie doesn't mention any wavelengths at all. He talks about frequencies and phases and how a particle that would have an oscillation would look like. So lacking an illustration, we started making our own ones. In this first one you can see two parts, a harmonic oscillator and a circle around it. The harmonic oscillator stands for the mass term in the equation, and the circle around it for the fact that de Broglie transforms its frequency as that of a clock. And a clock must be a closed system, because any disturbance of it will cause irregularities in its running. This was de Broglie's basic starting point. But in order to get some kind of boundary condition, you must have an oscillation that is spread out in space. De Broglie doesn't say so specifically, but in fact what he does is to introduce a second oscillation, which, because it is spread out in space, one can call a wave. And because it is a different oscillation, it has been given a different symbol. And in order to keep things apart, the second oscillation will be called the wave aspect, and the first one the particle aspect. This wave aspect has an as yet unknown and to be determined propagation velocity. And now, since we have two oscillations, one can impose a kind of a boundary condition by demanding that the phases of the two are equal, which for a stationary particle they naturally are. However, for a moving particle one gets into problems, because the particle aspect acts like a clock, so experiences time dilation or frequency lowering, while the wave aspect, according to de Broglie, transforms according to the gain of kinetic energy, that is, it gets a higher frequency, with the gamma being the factor familiar from relativity theory. Of these two frequencies being not the same, de Broglie writes that it intrigued him for a long time. That is, until we finally came up with the phase condition and a subsequent calculation for the phase velocity of the wave aspect, which he wrote down the other way around. Here we will put it in its proper order. Here's what he did in pictures. After time t, the electron has traveled distance x. The wave that started at the point of origin now has a phase retardation at x due to the time it needs to travel to x. The particle aspect, the clock, is assumed to be only retarded by the time dilation and not by any propagation, symbolized by the dashed line. Now require the two phases also to be the same at point x, as already has been implemented in the illustration. With a situation as in the illustration, the phases after time t then need to obey this expression, where u is the unknown propagation velocity of the wave aspect, and this already hides the desired result. Since here's what you get after substitution of the given transformation properties of the two frequencies. And this is the result after elimination of the common factors and the shifting of gamma to the left. The outcome for the unknown propagation velocity of the wave aspect can be seen on inspection. Here it is explicitly. Note that the symbol in the denominator is velocity, not frequency. This is the crucial result of de Broglie's deliberations. After using his boundary condition, he finds that this postulated wave phenomenon associated with the particle has to have this as its propagation velocity. And only now you can get to a wavelength, which is easy enough. But in de Broglie's thesis, this is mentioned only in a later chapter. The crucial historical note is that, as already mentioned, this is not in the order in which de Broglie formulated it. Possibly because he was so excited by his results for the propagation velocity that he started with this and proceeded to show that with it the oscillations remain in phase. Shown here is the central part of the derivation. It is quite difficult to trace back if you read it for the first time. For those who want to try, the link to the English translation of the thesis is given below. This somewhat confusing presentation was probably the reason that his ideas didn't catch on immediately, but it was Einstein, who was involved in the evaluation of his thesis, who promoted it with his colleagues, whereby it reached Schrödinger, etc. However, there is a simpler version of the derivation that also adds more insight. Its first known appearance is in a textbook on relativity theory by Peter Bergmann from 1942. See the full reference below. Here it is in pictures, starting with a stationary observer. De Broglie did not give a time delay to the clock frequency due to a difference in position, so for the stationary observer, the phase is the same all over space. And both the propagation velocity and the wavelength of the oscillation is infinite, leading to the expression for the de Broglie wave function as given in the illustration. Now go over to a moving observer. Then you have to apply a Lorentz transformation to the time according to this familiar one, changing both expression and picture. You get a sinusoidal waveform caused by the fact that the moving observer sees the phase of different points with a different delay, or in the exponential expression, due to the x term introduced by the Lorentz transformation. And there in the x term is the de Broglie wavelength. And note, this is not a relativistic effect, because that houses in the gamma, that has been omitted because it's negligible compared to the linear terms. And this is the operative term in the x part of the transformation. This transformation, and what the term means physically, gets clearer after a slight rearrangement. For now, compare this one to the Lorentz transformation of an electromagnetic wave. And in this one, the V divided by C term can be readily identified as the Doppler effect. So the v divided by c squared term is the linear Doppler term in the Lorentz transformation. In fact, take the Bryce boundary condition, the first expression, and substitute the value of nu w and u, giving the second one, with on the right hand side the same expression as that for the Lorentz transformation of time. So what de Broglie did, faced with the two quadratic Lorentz terms in numerator and denominator for wave and particle aspect, is to introduce a linear term in order to get a synchronous result, making a superluminal phase velocity the same as the linear term in the Lorentz transformation. So the two derivations of the wavelength relation, the de Broglie and the Bergmann versions, are physically identical. Both of them amount to applying a Lorentz transformation to a stationary oscillation with a wave aspect having an infinite propagation velocity. Now one may object to de Broglie's arbitrary looking choices, and they will be improved upon later, but the alternative that grew since the original was forgotten is undoubtedly much more arbitrary. This uses de Broglie's relation in the slightly different form shown. However, the change hides a conceptual one that turns out to be rather crucial later. Here, on this prestigious blackboard, is the first part of the derivation of the wavelength relation in its slightly altered form. As it states, for photons. Now photons are, is pretty well known and mentioned explicitly, massless particles, which is in contrast to the particle de Broglie uses, an electron, the one involved in atomic states, that definitely has a finite mass. Without mass, there is no de Broglie oscillation, so no de Broglie wavelength. But never mind that. Just postulate that the relation is equally valid for massive particles. There's quite a lot that you can say about that. Appropriate for the prestigious ones is to point to the analysis of the Poincare group given by using Wigner, which puts massive and massless particles in different symmetry classes. See the link below for further information. In practice, this has resulted in examples like this that highlight the arbitrariness of the procedure more clearly. And a second one. And a third. They all are conceptually the same as the prestigious one, but with less expressions and words. So de Broglie's, and especially the Bergmann version, would seem to be the better choice by some margin. However, there is a downside when viewed from the standpoint of regular physics. If you adopt de Broglie's version, you do away with the wave-particle duality it associates with the double-slit experiment. Because the wave-particle duality is an either-or case, and de Broglie's oscillation is tied to rest mass, so it is present permanently. And if the oscillation is present permanently, then so is its wave function. And if it had a finite wavelength, it would look as in this picture, even for a stationary particle. More like a wave-particle monism, both existing together, which is precisely how de Broglie himself talks about it. And one would also think that the choice between the standard or the de Broglie version is a take both sides choice. If you don't accept de Broglie's model, then don't use his wavelength relation. And if you do accept de Broglie's wavelength relation, then also accept his concepts, or explain why you don't need to. Or, slightly adjusting Einstein's words, do you really believe that an electron has no wave function when it has no velocity? Luckily, with the solution at the end of the series, the two concepts will also be reconciled. This solution will use both main concepts of de Broglie, the oscillation associated with rest mass and the Lorentz transformation. Finally, thus far, de Broglie's model is translational and unidirectional. For application to the atomic state, he came no further than the still familiar waves on the orbit model. The solution of that case was left to his successors, notably Schrödinger, whose equation is the subject of scrutiny in the next part.